Hi everybody, my name is Jo. I'm a lecturer in astronomy at the Open University, and I specialise in researching the atmospheres of other planets. And today I want to talk to you a little bit about my favourite planet in the solar system, which is Venus, and what went so horribly wrong to make it such an unpleasant place to be. Before we get started though, I've got a little experiment that I'd like you to join me with. It might not work so well today because it's not particularly warm and sunny weather. Could you just put your hands up if you like in the chat if you've got some chocolate chips and a jar and a plate and a bottle? Has everyone managed to bring those? It doesn't matter if you haven't, because, oh yeah, I've got a thumbs up. That's great from somebody. So what you need to do, it's very simple. So I've got my version here. I can't tip it up too much because the chocolate chips are going to fall off the plate. It doesn't have to be a bottle. It can be a glass jar. Anything that's clear that you can upend will work just fine. So I've got 3 chocolate chips and 3 on one side and 3 on the other here. Well, you can always try it again when you've got one. So it doesn't matter because we're going to try it all together and hopefully there'll be a result at the end. So I've got one little group of 3 chocolate chips on my plate on one side, and I've got one group on the other side. And all I'm going to do is take my lovely cut in half plastic bottle and put them over one of the groups of 3 and leave the other group uncovered. I'm just going to leave you for 2 seconds while I go and put this on the sunniest windowsill in my house, which is not currently very sunny, but we'll have to see what happens. So right, so I hope you've all managed to go and put your experiments on a windowsill or in the garden somewhere. I'll just give you a couple of minutes to do that. Then we'll get started with the talk. Right, everyone's muted. Yep. Okay, sorry. I've just got a message from the Facebook page. Just helping somebody join. Okay. Right, hopefully you've all got set up with your experiments. So I'm going to share my screen now and we will get on with the talk. Right, so what exactly did go so horribly wrong for Venus? Well, we've already set up our experiment. That's a better photo of my own setup that I did last week when it was much more sunny and it worked much better. So just before I carry on talking, maybe have a little think to yourselves about what you think is going to happen. So the experiment is which set of chocolate chips is going to melt faster. So don't share it in the chat, just individually have a think about what might be going to happen. So let's start by thinking about what makes Earth a particularly nice place to live. Well, one of the things that we think is really important if you want to have a planet that can host life is the presence of liquid water. Quite a lot of our bodies, in fact, any living organism is made of water. So we think that it's very important that it's there and also that it is a liquid. So that means, of course, that temperature is really important because if it's too cold, water won't be a liquid, it will be a block of ice. If it's too warm, on the other hand, it will evaporate. That means that it turns into a gas, which you can't see, so it just floats around in the air. And we don't think either of those are much use for living things, but liquid water is pretty great. So the temperature of a planet in our solar system depends broadly on how far away it is from the sun, because the sun is the major source of energy for everything within the solar system. It's sitting there in the middle of the solar system, it's burning hydrogen, and it's giving out lots and lots of energy. And if you get further away from the sun, you're going to receive less of that. So if we assume that we've got a planet in the sun that's a particular distance away that we call D, and we've got another planet that's twice as far away from the sun, so that distance is 2 times D, the planet over here is going to be receiving only a quarter of the amount of energy that the planet sitting just here is. So as you go further away from the sun in the solar system, you expect planets to go from being quite warm to getting increasingly colder. And that's actually what we do see. So these are the planets in the solar system. So you have to read left to right and then top to bottom. So the ones in the top row, these are the rocky planets that are in the middle. And these are Mercury, Venus, Earth, and Mars in that order. And then as you go further out, we have gas giant planets, which are much, much larger. These aren't shown to scale. And we've got Jupiter, Saturn, Uranus, and then finally the furthest planet out is Neptune. And we can do a calculation to estimate how hot each of these planets is just based on how much energy it's getting from the sun. So as you go further away from the sun, everything gets colder. And we can make some numerical estimates of temperatures. So for example, Mercury, which is the closest planet to the sun, we think that that's at about 152 degrees C. Now that's clearly far too hot for it to be a pleasant place. The average temperature on Earth is about 15 degrees C for comparison. Water definitely will not be a liquid on Mercury, so that's no good. The furthest rocky planet from the sun, Mars, now that's too cold. So Mars has a temperature of about minus 53 degrees C. So we're well in the territory of water just being solid ice. And then as you go even further away to the gas giants, so Jupiter, for example, about minus 163, and then Neptune, really far out, that's very, very cold indeed. That's minus 229 degrees. So we can make this estimate of temperature just based on the distance between the sun and the planet. So let's do this for Venus and the Earth. There's one other thing that we have to take into account, apart from the distance between the sun and the planet, and that is how reflective the planet is. So if a planet's really quite bright and shiny, then it might get quite a lot of energy, but it's going to reflect quite a lot of that back out into space. So any energy that gets reflected isn't going to be much use for heating the planet up. So actually, if we do this calculation for Venus and the Earth, then we get Venus coming out as slightly colder than the Earth, about minus 23 degrees C, Earth at minus 18. And the reason for that is even though Venus is closer to the sun than the Earth, it reflects a lot more sunlight. So Venus gets more energy, but it sends quite a lot of it straight back into space. So based on this estimate, Venus and the Earth are pretty much the same temperature, and also both quite cold. Remember, I told you that Earth's average temperature is about 15 degrees C, not minus 18. So why is that the case? Why do we have this apparently very cold temperature for both of those planets? And Earth being warmer seems very weird because, of course, it's actually further away from the sun. So that doesn't make a lot of sense. So what is actually going on? Well, the actual temperatures of Venus and Earth, well, Earth, as I told you, is about 15 degrees C. So that's not too different from the estimate that we came up with. But Venus, on the other hand, is 462 degrees C. If you were remembering the numbers from a couple of slides ago, that's quite a lot hotter than Mercury is, even though Mercury is closer to the sun than Venus. So that doesn't seem to make an awful amount of sense. How on earth did Venus end up so hot, so much hotter than the prediction we made? There's not some extra magical source of energy that only applies to Venus and none of the other planets. So what I'm going to introduce you to now is something called the greenhouse effect. Some of you might have a greenhouse in your garden, or if you've ever been to a garden centre, you might have seen them. And basically, all that a greenhouse is a structure that's mostly made of glass. And the reason that it's mostly made of glass is because glass is transparent to visible light. You know that, right? Because you can look out of the window and you can see the sunlight coming in. But the other really useful thing about glass is that it doesn't let infrared radiation through. Now, if you heat up something to, say, about 15 degrees, like on Earth, then the way that that something is going to try and lose the heat again is through infrared radiation. So if you have a glass house that lets sunlight in, and the sunlight warms up the air inside the house, but because the glass doesn't let infrared radiation through, the heat is going to stay trapped inside the greenhouse and it's going to keep warming up. And that's what you want, because the reason that you have a greenhouse there is to grow plants, and plants often like it to stay nice and warm. So you can grow, for example, things like sunflowers, or if you like, you can grow tomatoes and peppers and chilies, which my husband does. It turns out that our atmosphere, so that's the shell of gas that surrounds the outside of our planet, and it includes the air that you breathe, so the oxygen, which is very important, that enables you to survive. And, sorry. There we go. And that atmosphere is very much the same as glass. So it lets in visible light. Again, we know that because when we're out on a nice sunny day, we can look up in the sky and we can see the sun. But it's also very, very good at trapping infrared radiation. So you can see in this picture, this is showing the amount of stuff that can get out of the atmosphere or get through the atmosphere. So in the visible, it's most of it, but in the infrared, you can see that there are lots of gaps where nothing can get through at all. Sorry, can I ask you please to turn off your videos, because this is being recorded and it's going to be made public afterwards. So our atmosphere is very much like glass, and so exactly the same thing happens when sunlight comes in. So if sunlight heats up the atmosphere, heats up the planet, and that heats up the atmosphere in turn, but the radiation, the infrared radiation, doesn't escape. So that means that the planet continues to get warmer. It's a little bit like putting on an extra cardigan when it's a bit cold outside. So that means that we get from the original estimate for the temperature of the Earth, which was about -18 degrees, to the actual temperature, which is about 16 degrees. So the reason that Venus is so incredibly hot is because Venus has a much, much stronger greenhouse effect than the Earth does. Why is that? It turns out that if you make atmospheres out of different gases, then you have different amounts of infrared radiation being blocked. So our atmosphere is made mostly of nitrogen and oxygen. And neither of those things block a huge amount of infrared radiation, relatively speaking. Venus's atmosphere, on the other hand, is almost completely made of a gas called carbon dioxide. If you've heard about global warming at all in school, then you might have heard about carbon dioxide, because this is the gas that in very, very small amounts in our atmosphere is mostly responsible for global warming, which is due to the greenhouse effect. Now, Venus's atmosphere doesn't have just a little bit of carbon dioxide, it has lots. In fact, it has nearly 100 times as much as Earth's entire atmosphere of just carbon dioxide. So Venus's atmosphere is super good at blocking this infrared radiation, and that means its atmosphere can warm Venus up a lot. It's a bit like Venus is wearing about 100 woolly jumpers and Earth is only wearing one. So how did Venus end up like that in the first place? Well, we don't know for certain, but our best guess is that actually a very long time ago, when the solar system was quite young, before we had life and anything else going on here, Venus and the Earth were probably not too different from each other. Their temperatures wouldn't have been that different. And we think that Venus may well have had a water ocean at one point, just like the Earth did. Our water ocean, as well as providing a good environment for life to start, it's also quite useful for helping to control the temperature and the makeup of our atmosphere, because carbon dioxide dissolves in seawater. And on the Earth, sea creatures use it to make their shells. So little tiny things like shellfish and even smaller things actually make part of their outer skeletons using the carbon in the seawater. And then when they die, they fall to the bottom of the sea and they turn into rock, like limestone or chalk. And that rock actually contains a lot of the carbon that the Earth started off with, because we have that liquid water ocean. Venus probably had the same to begin with, but Venus has always been a bit closer to the sun than the Earth. So you've got two planets sitting there and they're both pretty similar, but Venus would have been a little bit warmer to start with because it was closer to the sun. And that would have meant that the water in the ocean started to evaporate. What happens when water evaporates? It turns into a gas, and that gas is called water vapor. So Venus ended up with an atmosphere that had quite a lot of water vapor in. Like carbon dioxide, water vapor is also really good at blocking infrared radiation. So we had the start of a greenhouse effect on Venus, and things warmed up a bit. Now, as things warmed up even more, then more and more of the water in the oceans began to evaporate. So there was even more water in the atmosphere contributing to the greenhouse effect. And this carried on and on and on until eventually all the water in the ocean had disappeared and evaporated and was in the atmosphere instead. No more water ocean. That means that there's nowhere for carbon dioxide to dissolve. So all of the carbon in Venus's budget ended up in the atmosphere. And carbon dioxide provides that nearly 500 degrees of greenhouse warming we have on Venus. At this point, it got so incredibly hot that all those little water molecules, which are made of hydrogen and oxygen stuck together, started to break apart because it was so hot and they got so much energy. And when that happened, the hydrogen and the oxygen actually escaped Venus's gravity and left altogether. So Venus can never be reversed. It can't ever go back to the way it was because there's not enough of those raw materials left to make a water ocean anymore. So this is an artist's impression, but it's actually pretty accurate of what Venus is like today. And what this is showing is a spacecraft that I used to work on called Venus Express, doing something called aerobraking in the upper part of Venus's atmosphere. So what it's done is it's dipped one of its solar panels down into the atmosphere and used the drag of the atmosphere to slow it down and measure how thick the atmosphere is. So Venus today is 462 degrees C. It's got so much carbon dioxide that its surface pressure is nearly 100 times as high as the surface pressure on the Earth. So it would be a little bit like being at the bottom of a very, very, very hot ocean on Venus rather than like standing on the Earth's surface. And it's also very, very cloudy. There's no such thing as a nice sunny day on Venus, but the clouds aren't made of water droplets like they are on the Earth. Of course they're not, because Venus lost so much of its water early on. They're actually made of something much, much nastier called sulfuric acid. So Venus is a really interesting planet, but it's not somewhere that we would ever want to visit. So one of the things that I work on now, which I find really exciting, is looking at planets that orbit stars other than our sun. And we call these planets exoplanets. One of the questions that we're really interested in answering is which of the outcomes is more likely. If you have a rocky planet at about the right distance from its star, is it more likely to go Earth or Venus? Is it going to be a nice place to live, or is it going to be a horrible place to live? And we found some systems of rocky planets orbiting other stars, and one of these, this is an art, again, it's a picture drawn by an artist of a system called the TRAPPIST-1 system, and that has 7 rocky planets, and the ones sort of in the middle of that picture are, we think, are reasonably similar sorts of temperatures to the Earth. So at the moment, we don't really know what conditions are like on those planets. We're just making an estimate, like we did at the beginning of the talk. But we'd really love to know whether these planets look more like Venus or like the Earth, or maybe like something completely different that we don't have at all in our solar system. So I'm sure you're wondering what happened to the chocolate chips. Now, I recorded the rest of the talk yesterday and the weather was not very good. I thought I'd have another go today, but actually I'm afraid we're going to have to revert to here's one I did earlier. So I did the same experiment last Friday when it was really nice and sunny out in the garden. And after about 20 minutes, this is what happened to the chocolate chips. So this is a picture of the chocolate chips on the plate. You can see that the three that were covered by the bottle completely melted. The three that were not covered up really hadn't melted at all. They hadn't even got a little bit soft. So what this demonstrated was that the glass bottle, the plastic bottle was trapping the infrared radiation coming from the surface of the plate and from the chocolate chips and preventing it from escaping again, whilst letting the sunlight get through, which is what was heating the chocolate chips up in the first place. So that was actually a really nice demonstration of how the greenhouse effect works. I think it's definitely worth trying again if the weather is a little bit better. It also serves to illustrate the fact that you do need something producing the heat in the first place. So you do need there to be enough sunlight for this to work properly. Thanks very much for joining me with this, and hopefully I'll see you another time for another chat about something to do with space.